Hi boys and girls, this is lecture 6.9, the topic inverse trigonometric functions, differentiation, and this will be part 2 of our discussion. In this lecture, we're going to do a couple more examples utilizing derivatives of inverse trigonometric functions. So to refresh your memory, I have supplied the list of derivatives of inverse trigonometric functions here. In this first example, I'm asked to differentiate y equals arcsine of x plus x times the square root of 1 minus x squared. I'm going to rewrite this equation, making one slight adjustment. Y equals arcsine of x plus x times the quantity 1 minus x squared to the 1/2 power. So I'll have to use the product rule for this second term. Therefore, my derivative will be y prime equals 1 over the square root of 1 minus x squared plus the first times the derivative of the second function, 1/2 times 1 minus x squared to the negative 1/2 power, and then times the derivative of what's inside, which will be negative 2x, plus the second function, 1 minus x squared, to the 1/2 times the derivative of the first, which is 1. Now let's simplify this a bit. Y squared equals 1 over the square root of 1 minus x squared. This term is going to drop to the denominator. 1/2 times 2 is 1, so I'm left with negative x squared in the numerator. Negative x squared over the square root of 1 minus x squared. Then plus 1 minus x squared to the 1/2 power. These are like terms, so let's combine them. Y squared equals 1 minus x squared over the square root of 1 minus x squared plus the quantity 1 minus x squared to the 1/2 power. Now if we think of this quantity as being raised to the 1 power, and this is the same quantity raised to the 1/2 power, we can subtract those exponents. 1 minus 1/2 is 1/2, so that becomes 1 minus x squared to the 1/2 power, and it's being added to the exact same quantity, 1 minus x squared to the 1/2 power. Since these are like terms, I have two of them, 2 times the quantity 1 minus x squared to the 1/2, or this could be written as 2 square root of 1 minus x squared, and that is your simplified derivative. In this example, we're going to find the derivative of an inverse trigonometric function in order to locate relative extrema. Let's find the derivative of y equals the quantity arctan x squared. That will be y prime equals 2 times arctan of x to the 1 power times the derivative of arctan, which is 1 over 1 plus x squared. We can write this as 2 arctan of x over 1 plus x squared. Of course, we need to set this equal to 0 in order to locate critical numbers. And since this is a rational expression, we need to just examine where the numerator is equal to 0. And dividing both sides by 2 gives me 0 equals arctan x. Another way to write this expression is to say tangent of 0 equals x. And we know, of course, that tangent of 0 is 0. So we have a critical number at 0. Let's set up some intervals to determine what's happening on either side of 0 to discover whether 0 is a max or min value. I know we're looking at the graph and we can see what it is, but as always, we want our analysis to support our graphical conclusions. In the first interval, I'll use -1 as a test value, and I'll use +1 as a test value in the other interval. When I plug -1 into the first derivative, I get -0.785, just using my calculator, and that is a negative number, which means to the left of 0, our function is decreasing. When I plug +1 into the first derivative, I get a positive 0.785, which again is a positive number. That's all I really need to know. And that means that the function is increasing to the right of 0. This confirms that 0 is a minimum value, and the only other thing we would like to know is the y value associated with the x value of 0. So let's go back to the original function and find out what y value goes with an x value of 0. We've already seen that arctan of 0 is 0. Of course, 0 squared is 0. So the only extrema on this function is a minimum value at 0, 0. Before we close out the Unit 6 lectures, let's have a brief discussion about elementary functions. As mathematics has developed during the past few hundred years, a small number of elementary functions has proven sufficient for modeling most phenomena in physics, chemistry, biology, engineering, economics, and a variety of other fields. An elementary function is a function from the following list, or one that can be formed as the sum, product, quotient, or composition of functions in the list. These elementary functions come in two categories: algebraic functions and transcendental functions. The algebraic categories that we've discussed: polynomial, rational, radical. The transcendental categories: logarithmic, exponential, trigonometric, and inverse trigonometric functions. With the differentiation rules introduced so far, you can differentiate any elementary function. Below is a summary of these differentiation rules. So let's go back to the beginning. The derivative of a constant times a function u is that constant times the derivative of the function. Here is the sum and difference rule, the product rule, the quotient rule. We learned that the derivative of a constant is 0. Here's our friend the power rule. The derivative of x equals 1. We even learned to take the derivative of an absolute value function, the natural log function, e to the u, and we learned to take derivatives of logarithmic and exponential functions of bases other than e. Here are our 6 trigonometric functions and our 6 inverse trigonometric functions. We've come a long way. That's it for today's lecture, and that concludes the Unit 6 lectures. Since we're learning to explain how we get our answers, I thought we could use a little help from Foxtrot. God bless you, boys and girls.